everyone. Hello. Welcome to the first Ivy Talk of 2023. We're very excited to have everyone here this evening. I am Susie Farmer, the Education Director at Ivy Creek Foundation, and it is my pleasure to welcome all of you all tonight. Professor Callan Bentley is speaking with us this evening about the geology of Ivy Creek Natural Area and the surrounding area. Professor Bentley is an associate professor of geology at the Piedmont, Virginia Community College here in Charlottesville. He is a fellow of the Geological Society of America. The National Association of Geoscience Teachers recognized him with the James Shea Award. He's also won the Outstanding Faculty Award from the State Council on Higher Education in Virginia. He has many other awards, too many to list as well. So we are very excited to host him this evening. Before we get started, just a couple of housekeeping items before we begin. Please mute yourselves if you have not already done so. And this is being recorded and it will be posted to our website in just a few days. And if you have any questions, we will have time for a Q&A at the end of the talk. So you can just put your questions in the chat box and we'll get to them at the end of the talk. So now I'll turn it over to Professor Bentley and we'll learn all about geology this evening.
Great. Thank you, Susie. Hi, everybody. I'm really glad to see such a great turnout this evening. Here in Charlottesville, it's a dark and rainy evening, and so it's a good evening to be cuddled up inside, hopefully on some comfy furniture and with a warm cup of tea and in front of the glowing computer screen. All right, so what we're going to do tonight is we're going to talk about geology, specifically the geological history that is written in the rocks of Ivy Creek. Now, Ivy Creek, as you may well be aware, is part of Virginia, and Virginia is part of the United States of America, and the United States of America sits on the North American continent. So really what we're doing here tonight is we're looking at the geological history of the North American continent. We're going to look at 3 specific episodes in the history of that continent. Now, the oldest part of our continent is mostly exposed up in Canada, though there are a few parts that dip down into the good old US of A. There are also old parts of the continent that are covered up by a sedimentary blanket. And we call the exposed old parts of the continent the shield and the covered up parts of the continent the platform. Together, these make up the craton. And craton basically is a word that means like the stable, long-term stable nucleus of the continent. There's plenty of stuff here that's not labeled as the craton, including where we are now in Virginia, or at least where I'm broadcasting from in Virginia. So where did all that stuff come from? Well, in short, it was added on later, okay? It was accreted. That is the term of art for taking a block of rock that started off somewhere else and then smashing it onto the margin of a continent, okay? So you can see that there have been various accretionary episodes in the history of the North American continent. The old parts here are colored purple and gray and red. And then you can see there's a light gray that was accreted, then a green that was accreted. And then this orange stripe, that's where our story is going to begin, the Grenville province. So we're going to look at the accretion of the Grenville province, and then later we'll look at the Appalachian stuff that gets tacked on after that. Okay, so this is like making a snowball in the winter. You start off with a small snowball, and then you add snow on the outside, and you build up a bigger and bigger snowball through time. Okay, so we're going to begin our story about 1.1 billion years ago, when this strip of land got accreted or tacked onto the North American continent, okay? It's colored orange here as well, and this is called the Grenville province. You will notice that it runs from Labrador and Newfoundland in Canada all the way down through the Adirondacks of New York, through the Blue Ridge of Virginia, and all the way down to the Marathon Mountains of West Texas, and even portions of Mexico. And you can see in this little inset here, even portions of Scotland contain these Grenville age rocks. So where did they come from and how did they get here? Well, the answer to that question was deduced by a Canadian geologist a guy named J. Tuzo Wilson. He was at the University of Toronto, and Tuzo Wilson studied the Appalachians. Specifically, he did most of his field work in Newfoundland, and we'll make a little side trip from Ivy Creek Natural Area to Newfoundland later in the talk. But he came up with the idea that the Atlantic Ocean, what he called the Atlantic Ocean, closed and then reopened. Nowadays, we use slightly different terms for it, but the basic idea is still there that basically early on, a supercontinent formed. Then that supercontinent broke apart into various continental fragments. Then those came back together. They made another supercontinent, and then that one broke apart. All right, so that's shown here as a series of little cartoons on the side, and we'll look at these in more detail later. But the very first episode to be recorded in the Appalachian Mountains is this Grenville orogeny. Orogeny. That's a word that means an episode of mountain building. All right, a time when mountains were constructed through continental collision. After the Grenville orogeny, there was an episode of rifting that broke that continent apart, and that opened up a new ocean basin. All right, what you might call the Proto-Atlantic, or we'll learn to call the Iapetus. The Iapetus then closed, and we got another supercontinent. This one you may have heard of, Pangaea. All right, and Pangaea was a supercontinent that formed when the Appalachian Mountains were first made. Then Pangaea broke apart, we got the Atlantic Ocean, and that's how we ended up where we are today. All right, so that is thanks to J. Tuzo Wilson. We call this cycle of supercontinent formation and breakup a Wilson cycle in his honor. Okay, so here is a crude geologic map of the Commonwealth of Virginia. This is put together by Chuck Bailey at the College of William & Mary, and I see we've got a couple of William & Mary professors emeritus on the call. That's great to see. Virginia can be divided up into a series of provinces. We call these geologic provinces. Basically from Richmond East, it's the coastal plain. Out in the Great Valley, it's the Valley and Ridge province, the Appalachian Plateaus, that's where you'll find the coal. But right in the middle, we've got the Blue Ridge and the Piedmont. All right, and so I'm talking to you from Piedmont, Virginia Community College, and you might think, well, gosh, that means he must be in the Piedmont Geologic Province. But unfortunately, I hang my head in shame. It's not true. We're in the Blue Ridge Geologic Province here, but we're real close to the Piedmont. So we're going to explain how those fit together here. The stories of the Blue Ridge and the Piedmont are intricately and intimately linked. So this Grenville episode of mountain building, this Grenville orogeny, we said it made a supercontinent. The name of this supercontinent comes from the Russian word for homeland. All right, it's called Rodinia. All right, so Rodinia is a supercontinent that formed around 1.1 to maybe 1.0 billion years ago. That's billion with a B. So a 1 with 9 zeros after it. A very, very, very big number, okay? But that's still not even halfway back through Earth history. So this is still relatively recent news. All right, so this Rodinia supercontinent, if you take a look at it here on this map, it might be a little bit difficult to locate where Virginia is here, but I'll go ahead and put a star on it right there. So this part of Rodinia, sort of the middle or the nexus of Rodinia, that is ancestral North America. You'll notice that it's much further south than it is today, and that it's rotated relative to its modern day position. So this is like Texas over here in the west, and this is like Newfoundland over in the east. This is like Alaska over here in the north. So basically the whole thing's got to rotate about 90 degrees and move north to get it where we find it today. Off the, what was then the southwest coast, what is today the east coast, we've got Amazonia and the Congo. All right, these ancient cratons that are now parts of other continents. We've got Australia and Antarctica and India over on the other side of North America. So that is a very different configuration of the land masses compared to what we have today. Okay, so what's the evidence that this Grenville orogeny ever took place? Like, why should you believe me when I say that there was an episode of mountain building here around 1.1 to 1.0 billion years ago? Well, the answer is written in the rocks. Mother Nature has a very endearing habit of writing her autobiography in the language of rock. And my job as a geologist is to translate that language so that the rest of us can understand it. So, this episode of mountain building is recorded in granites and granite gneisses in the Blue Ridge geologic province. Granites are igneous rocks. They form from molten rock. This molten rock, or magma, cools down very slowly deep underground. Because it cools down slowly, it grows nice big crystals that are really easy to see with the naked eye. Volcanic rocks don't pull that trick. They have very, very tiny grains because they cool off super fast. A granite gneiss looks a lot like a granite, except all those minerals are smeared out into little stripes, all right? So those stripes basically reflect the fact that this is a granite that got squeezed during mountain building, okay? So here's an example of one of those granites. This is the Pedlar Formation. It's a granite gneiss that we find in Shenandoah National Park. All right, I seem to have a couple of random little yellow stripes over there. They're bugging me. And so, nope. Let me go ahead and try and erase those. I don't have an eraser. Okay, never mind. I'm going to skip that. I'm going to deal with it, and you can too. Okay, so the Grenville orogeny gets its name from a little tiny town in Quebec. It's like, why would you name a mountain building episode after this little tiny middle of nowhere village in Quebec? Well, that's just the place where this mountain building episode was first described. All right, and it's not just limited to Grenville, Quebec. We find it all over the place. Here's an example of an outcrop you can find on the Blue Ridge Parkway, down Roanoke Way, and you can see a couple different granites here. Notice that the one on the left is kind of pink, the one on the right is a little bit more grayish green, all right? These rocks are the sorts of rocks we would expect to be forming today underneath something like the Himalayas. All right, so the Himalayan mountains, where India is crashing into Eurasia, is a modern day analog for what we think happened in Virginia around 1 billion years ago. All right. One of our distinctive granite-like rocks that we have in the Blue Ridge of Virginia is this one. It's called Charnockite. It's named after Job Charnock, who was a British colonialist, was charged with founding Calcutta. And he was buried in a tomb made of this rock. And so they named it after him. Turns out Virginia's got a heck of a lot of this charnockite. It's really distinct because of its green mineral pyroxene. All right, so on a fresh surface, you get this kind of green color. And on its weathered surfaces, you can see that it rusts. So it gets this sort of orangey kind of exterior. This is why geologists carry rock hammers with us out in the field, right? We want to go and we bash off that weathered rock and we look at the nice fresh rock underneath. You're not allowed to do that at Ivy Creek Natural Area, okay? So look, but don't hammer. Another example of a Grenvillian basement granite is this one. This is from Nelson County, just down at Woods Mills. This one's really rich in the mineral biotite, which gives it a much darker color. Here's one that you might have seen if you've ever had the experience of climbing Old Rag Mountain. It's got a lot of feldspar in it, which is this sort of peachy colored mineral, but then a sort of bluish quartz, all right, that's very distinctive to the Blue Ridge Basement Complex. This is actually the youngest of any of the Blue Ridge Basement Complex rocks. It's only 1.04 billion years old. If you're interested, I can talk later about where these numbers come from, how we date these rocks. But for now, I think you'll just have to trust me that it's about that age. Okay, so where can you see Grenvillian granites at Ivy Creek Natural Area? Well, this is one spot. If you've ever hiked around the trails at Ivy Creek, you've probably crossed the river, or not the river, this little creek right here. That's called Martin's Branch, and this is where the red trail crosses Martin's Branch. This is the outcrop immediately upstream from that little crossing, all right? So that is rock that is 1 billion years old and originally formed as magma, molten rock deep below Earth's surface. And it's been solid for over 1 billion years. Okay, Here's another example. This is at the Ragged Mountain Natural Area, another great place to go and walk around in Charlottesville. And you can see the contact here between two very different looking granites. One more fine-grained and light-colored, one more dark-grained and dark-colored and coarse-grained. Another granite that we have, or granite-like rock, is a weird one. This one is named for Nelson County, and it is called Nelsonite. And for a few years now, Nelsonite has been our state rock here in Virginia. We have a state rock, and that legislative accomplishment was achieved by students here at Piedmont Virginia Community College under the guidance of my predecessor, Larry Tiesi, and our government professor, Connie Jorgensen. So what's weird about Nelsonite is it doesn't have the usual mix of silicate minerals like feldspar and quartz. Instead, it's all apatite and ilmenite. So it's basically a super titanium-rich rock, and that led to it being mined. So most of the outcrops of Nelsonite are long gone. They've all been carted off and turned into titanium, turned into maybe paint or the white colored filling in Oreos. Those are titanium oxides. We really like titanium for its white color. Okay, now here is another one of these Grenvillian basement rocks. This one has something different though. I'm taking off my sweater because I'm getting warmed up. It's that time of the lecture, people. All right, so this is in my backyard. All right, this is a pavement outcrop in my backyard. And like any good homeowner, I have pressure washed it so that you can get a nice look at its details here. The key thing that I hope will jump out at you is that the minerals are all lined up. In other words, this is not a granite, this is a granite gneiss, all right? And that indicates that it got squeezed during the Grenville orogeny and it developed this very pronounced foliation, all right? Foliation is like folio, like a book, all the pages are lined up in the same direction. It's like that with the minerals in a granite gneiss. All right, so here's an example, a little cobble I found last weekend hiking around at Ivy Creek. You're basically looking at the plane of foliation here. So this is kind of like looking at the cover of a book, all right? But it's got a flakiness that runs through it caused by that alignment, and that alignment was due to this ancient mountain building episode. Here's another cobble. See the lines that go across from lower left towards upper right? I'll go ahead and annotate them there so you can see them. That's the foliation. Okay, so this foliation is caused by this squeezing, all right? So as Amazonia or the Congo Craton, whichever one of those it was, squishing into us here, that squeezed these granites and caused all their minerals to line up in that distinctive way. So this is a map of Rodinia drawn for about 700 million years ago. You can see again, North America is sort of at the center of Rodinia. You can see that there are pre-Grenville mountain belts that stretch through Canada and Siberia and Australia. But what I really want to call your attention to is the orange, all right? All that orange shows you where there's Grenville age mountain building. You have it in Scandinavia, you have it in Greenland, you have it in Amazonia, you have it in the Congo, in the Kalahari, Madagascar, India, Antarctica, Australia. All of these different places around the world smashed into something around 1 billion years ago. And so that's what causes us to think they all smashed into each other, all right? That way we don't need to posit crashes into objects that no longer exist. And that's where we come up with this idea of Rodinia. All right, so you are here. Okay, so the Grenvillian orogeny can actually be broken down into several smaller events. There's an earlier cycle called the Shawinigan orogeny, a slightly later one called the Ottawan, and then a very youngest one called the Rigolette. All right, so these episodes are deduced through the presence of certain minerals that we can date, specifically the mineral zircon, all right? Zircon is a zirconium silicate mineral, meaning it consists of the elements zirconium, silicon, and oxygen, just those three. Except it's not just those three, because every now and then a uranium substitutes for the zirconium. And so that uranium starts to provide a clock through radioactive decay, and it builds up lead in the zircon crystal. The older the crystal is, the more lead it contains. All right, so this is a look at, this is a histogram showing the distribution of ages found for zircon crystals in one study of the Appalachians. So what I want you to zero in on here is at the bottom, there's this 1100 MA date. 1100 million years ago is another way of saying 1.1 billion years ago. And what I want you to notice here is that there's a big peak in zircons, this blue peak here right before that 1100 and another peak right after it. So those are two of those cycles, the Shawinigan and the Ottawan orogenies, that collectively tell us this is a Grenville aged rock. Maybe that's a little too esoteric, you know, these sort of plots of data and, you know, counting up these ancient ages. Maybe something that is a little bit more approachable is the petrified forest. All right. You didn't think you were going to the petrified forest today, did you? Well, the petrified forest out in Arizona is actually buried in Appalachian sediment. So these trees that have been turned into rock, they were buried underneath sand and mud. And we know that that sand and mud came from the Appalachians. How do we know that? We look at the zircons. All right. Some of that sand and mud are these little crystals, these durable little timekeepers called zircon. And again, they show us a peak right there at around 1.1 billion years ago. So there's nowhere else that could have come from. Couldn't have come from California, couldn't have come from Alaska, couldn't have come from Minnesota, all right? It came from the Appalachians. That's the only game in town when it comes to that date. Okay, so we made Rodinia. It's time to move on to phase 2, breaking Rodinia apart, all right? Supercontinents, like all good things in life, they just don't last. All right, so you can have them for a while, but then they break apart. So when Rodinia broke apart, Africa pulled away, Europe pulled away, and it opened up a brand new ocean basin in the wake between these two departing continents. That ocean basin is named the Iapetus Ocean. All right, this is the one that J. Tuzo Wilson called the Proto-Atlantic, but I call it the Iapetus Ocean. Iapetus is actually a very clever name because the Atlantic Ocean, oh, that's our location, by the way. The Atlantic Ocean is named for Atlas, the Greek Titan who held the world on his back. Actually, I guess technically he held the world up, but he's usually depicted nowadays as holding a big globe on his back. The Atlantic Ocean is named for Atlas. The Iapetus Ocean is named for Atlas's dad. Atlas's father was Iapetus. All right, so we named the ocean that came before the Atlantic for the Greek Titan who came before Atlas. We're so classical. All right, so what is next in our story that shows this breakup of Rodinia and the birth of the Iapetus Ocean? Well, this is a diagram, again, by Chuck Bailey at William & Mary, showing the stack of rocks that we have in the Blue Ridge Geologic Province. So Charlottesville is over on the right side of this diagram. Shenandoah National Park is over on the left side of this diagram. Left is west, right is east. All right, so we're looking at an east-west cross-section through the Blue Ridge. Notice down here at the bottom, we've got our Grenvillian aged rocks. We've got our older ones that have the foliation. And then we got the younger ones like the old rag granite that don't have a foliation. So granite gneisses and granites. I'm going to skip the Robertson River Igneous Suite because it's a little bit weird and it's not pertinent to Ivy Creek, but that's another wrinkle on the story. What I want you to notice next is that overlying those deep crustal rocks are sedimentary layers. And these sedimentary layers go by different names depending on where you find them. In the Western Blue Ridge, we call it the Swift Run Formation. In the Central Blue Ridge, we call it the Mitchum's River Formation. And in the Eastern Blue Ridge, we call it the Fauquier Formation or the Lynchburg Group, depending on whether we're closer to Northern Virginia or closer to Southern Virginia. All right. So in Charlottesville, we call it the Lynchburg Group. So I'm going to introduce you to these sedimentary layers. And then after I've given you all the details you need to know about them, we're going to move up and we're going to take a look at the layer overlying that, the Catoctin Formation, all right, which is part of this same rift-related sequence. So basically one of these is going to be a sedimentary layer and one of these is going to be a volcanic layer, but they basically formed at about the same time due to the same tectonic circumstances. All right, here's a look at the Swift Run Formation. At the bottom of the screen, you see what used to be mud and is now a mud rock. At the top of the screen, you see what used to be sand and is now a sandstone. All right. Notice that the sandstone is made out of the biggest particles right here where it meets the muddy rock, and then it gets finer going up. That's the signature of an underwater landslide, what we call a turbidity current. It produces a graded bed where the largest particles, because they're the heaviest, settle out first. And then the smaller particles take a little bit longer to settle out on the bottom. These large particles are chock full of the mineral feldspar. And feldspar is not really a stable mineral at Earth's surface. It's not like quartz. If you leave feldspar lying around in your backyard for too long, it'll turn to clay. It'll rot. Okay, so that is evidence that this sediment was not, it didn't spend much time on the surface of the Earth. It was produced through weathering. It traveled a short distance. It was dumped and was buried. All right. It didn't spend thousands of years being gently washed by the waves. All right. Because if it had been, you wouldn't have all that feldspar there. Okay. The feldspar is the signature of it being immature. Here's another look at another sample of the Swift Run Formation. This is from Shenandoah National Park. And again, we have one of these graded beds showing an underwater landslide. So a lot of mud and a lot of this immature sand. Another outcrop, this one's at Patricia Byram Park. This is a Albemarle County park that is right up against Shenandoah National Park's eastern margin, up by near where I live, up near Free Union. And you can see here that we've got a bunch of different features in this outcrop. And what I'm going to do is I'm going to rotate the right image 90 degrees. Okay, that's going to allow us to look at these features in their original sedimentary orientation. So the key thing to note here is that we have these layers that alternate grain size. These are sedimentary beds, each representing a separate depositional event. And within some of those beds, we've got these layers that are highlighted with green here. That's cross bedding. Cross bedding is a feature that forms on the downstream side of a migrating ripple as it moves in a directional current of water, like a river. So this is evidence that the Swift Run Formation was deposited not in the ocean, but actually in a terrestrial river that was feeding into the Iapetus Ocean. All right. And you can also see that there is a foliation highlighted here in red, which is what makes these little groovy lines you see moving from upper left towards lower right in the original unannotated image. And that foliation is not due to the Grenville orogeny, which is at this point a distant memory, but instead will be imparted later due to Appalachian mountain building, which is still to come. Now at Ivy Creek, this is what you're likely to see. This is a cobble of the Lynchburg Formation. This is a sandstone. So if you pick this up, you see lots of little sand-sized grains, and I hope your eagle eyes will pick out that there's a lot of feldspar in there. So again, this is an immature sandstone. All right, not the sort of thing you'd expect to see being laid down today at a place like Virginia Beach. All right, this is the sort of thing you'd expect to see being laid down today at a place like Death Valley. All right, a modern day rift setting. Here's another example. This one's a little bit finer grained, less sand, more mud. All right, and that mud is dominated by the mineral clay. Let's see if I can make this play again here. I might have to back up. Let's see. And we'll go to it again. All right. What I want you to keep your eye out for is a shimmery gleam. All right. There's a whole bunch of little mica crystals in this rock, and those micas used to be clay. All right. Mica is not a typical mineral that we get in sedimentary rocks. Clay is, but when you get clay really hot and bothered, the atoms that make up the clay reorganize themselves and they make mica instead. All right, so it gives a silvery kind of glint to the rock, and that's a new foliation. That's going to be that Appalachian foliation. All right, so here's an example of a boulder. This is like by the big dead tree as you're climbing up the hill from Martin's Run or whatever that little creek is that we talked about earlier. And you can see that there's a very prominent foliation going through this Lynchburg Formation meta sandstone. All right, so that's a later Appalachian overprint. Okay, so those two rocks I just showed you were located here. That's where the big dead tree is. I saw a red-tailed hawk when I was there last week. And then the shimmery, glimmery one was over here on the Peninsula Trail. Okay, so modern day analog for what Virginia would have looked like at this time. This would be the Neo-Proterozoic, call it about 600 million years ago. Is it would have looked like modern day East Africa? East Africa, Kenya, Tanzania, Ethiopia, Eritrea, Djibouti. All right. These are places where the African continent is being stretched apart. It's already spawned off little chunks of continental crust. Africa flung Madagascar off a while ago. Arabia is a more recent reject from Africa. And now Africa is in the process of getting rid of Somalia as well. So it's breaking off and it'll eventually become an island, kind of like Madagascar, out in the Indian Ocean. So here's a look at the Afar Triangle region. This is in basically real close to the Red Sea and the Gulf of Aden. There's a fault that runs along each of these dotted lines, and then you can see sediment coursing down from the neighboring highlands and forming this big apron of sediment, a series of alluvial fans all along the margin of this rift valley. That sediment is chock full of feldspar. It was weathered out of a rock here, it was transported a couple of kilometers, and it's going to get buried over here before it has a chance to rot and become clay. You also see in the lowest lying areas, water has pooled, all right? So that water would be relatively calm water. That's the sort of place where you would deposit mud, whereas on these alluvial fans, the mud would keep moving due to the fast-moving currents. And of course, the big glaring thing that's right in the middle of this picture are these big black blotches. Those big black blotches are lava, all right? Lava rock called basalt. And that's where our story goes next. The eruption of huge volumes of mafic lava. Mafic is a word that geologists use to describe lava that has a certain character. It is silica poor and it is iron and magnesium rich. And that composition gives it a characteristic dark color. So one place where you can see basalt erupting today is the big island of Hawaii, right? There was a big lava flow on Mauna Loa just last month. I think Kilauea just filled up again, Halemaumau, last week. So that's a place where a lot of basalt is being produced. This picture here comes from Iceland, another place where you have the crust stretching. In other words, it's a divergent plate boundary, and that decompresses the mantle rock underneath. That causes the mantle rock to sweat out this basaltic lava. So here's a crack in the earth. Underneath this would be some sort of a crack that extends down to some distance, and then lava is flowing up through that crack, fountaining out onto Earth's surface, and then you can see it flowing away as sort of a flood here in the foreground. So that's what made the Catoctin Formation, all right? The Catoctin Formation, pictured here at Point of Rocks, Maryland, but present all over the place on Skyline Drive in Shenandoah National Park, and making up Carter's Mountain just out my window here. And the rock underneath my campus is the Catoctin Formation, all right? This is a series of lava flows that erupted around 600 million years ago as Rodinia was breaking apart. Now, the Catoctin Formation is not basalt anymore. All right, so it must have been basalt before, because nowadays what it is greenstone. And greenstone is a metamorphic rock with basalt as its parent rock. So in other words, we got a lot of greenstone around today that we call the Catoctin Formation, but the only way to get a greenstone is to take a basalt and then metamorphose it. So that metamorphism is going to happen during the Appalachian mountain building episode. But it used to be basalt, all right? Jet black, fine-grained lava rock. Here is the contact between the Grenvillian basement rock and the overlying Catoctin Formation. This is an outcrop near Stony Man in Shenandoah National Park. And right here near my finger, you can see there's a line that separates the lighter colored, coarser grain material below from the darker colored, finer grain material above. All right, so the bottom rock here is 1.1 billion year old Grenvillian granite gneiss, and the upper rock is the Catoctin Formation. And again, that's around 600 million years old, which means along that little yellow line, we are missing 500 million years of geologic time. We're missing 500 million years right there. All right, there's no record of it. That's a time when the Grenvillian mountains were erased by erosion. And it was only after 500 million years had passed that sediments and lava started to pile up on top of their eroded roots. Now, this Catoctin formation has some pretty spectacular characteristics. One of my favorites is columnar jointing. So this is an outcrop on the Limberlost Trail in Shenandoah National Park, and you can see that there's a distinctive pattern to the cracks here. They make a series of hexagons in the rock, and if you look at this from the side, those hexagons are just the tops of basically huge prisms that extend downward into the rock. These are cooling columns, and we also find cooling columns at places like Devil's Tower in Wyoming. I think it's in Wyoming. Yeah, right there on the border with the Dakotas. Yeah, Wyoming. So that's the picture over here on the right. Those of you who've seen the Spielberg film Close Encounters of the Third Kind will be familiar with Devil's Tower. The picture over here on the left is a Led Zeppelin album. Its cover photograph shows the Giant's Causeway in Northern Ireland, another classic place that shows these awesome cooling columns. The idea here is that the lava flowed out on the landscape, it cooled down, became solid, but it was still hot rock. Hot rock takes up more space than cold rock, and so over time as it cooled off, it shrank a little bit. It contracted, it became more dense, and that caused the basalt to pull away from its neighbors, and so these equally spaced centers of contraction opened up a series of fractures in between them, and then those fractures propagated down through the lava flow, dividing it up into a series of these columns. So here's a loose column that a friend of mine picked up on the trail up Little Devil's Staircase. This one only has 5 sides rather than 6, but it's still a perfectly legit column. And here's a whole bunch of them. This is up on top of Compton Peak in the northern part of Shenandoah National Park. This is about a 1-mile hike from Skyline Drive. And you can see these really awesome world-class columns. Another primary volcanic structure that we see in the Catoctin Formation is fossil gas bubbles. When lava erupts, it goes from being deep underground, where it's under tremendous pressure, to being up here at Earth's surface, where the pressure is much less. This causes any gases dissolved in the lava to come bubbling out of solution, and those bubbles may pop, in which case those gases are released to the atmosphere. What you're looking at here is evidence of bubbles that didn't pop. If the bubbles never get a chance to pop, they get preserved as Swiss cheese style holes in the lava rock, all right? And later on, groundwater moving through the Catoctin Formation can fill those holes in with minerals. So all the little white specks you see here, all the things that look like little polka dots, those are filled in ancient gas bubbles. So those little structures formed around 600 million years ago when the Catoctin Formation erupted, and then they were filled in sometime after that. We call the original name of the gas bubbles vesicles, and when they've been filled in, this is a great term, they're called amygdules, which comes from the Greek word amygdala, which means almond. So some hungry geologist looked at this outcrop and thought it looked like a nice almond-studded pastry. Another neat feature of the Catoctin Formation is the presence of some rocks that are not lava flows, that are in fact volcanic mud flows. Volcanic mud flows go by an Indonesian term, a Bahasa Indonesian word called lahar, all right? When Mount St. Helens erupted in 1980, most of the people who were killed by that eruption were not killed by the initial blast or by lava flowing. They were killed by volcanic mud flows that came down the valley of the Toutle River. All right, so volcanic mud flows are fast moving, faster than lava, and they often pack a pretty severe punch. You can see that by the size of the pieces they pick up. So here are all these chunks that are included in this ashy matrix. So this is the signature of an ancient volcanic mud flow, or lahar. We call it a volcanic breccia. Here's another example of a volcanic breccia, this one at Franklin Cliffs in Shenandoah National Park. And you can see here that the ash has all been turned green by later Appalachian metamorphism. All right, this is the same greening episode that turned the Catoctin Formation basalt into greenstone. All right, it's a mineral called epidote. Very eye-catching. I think this is a good-looking rock. All right, Here's Stony Man in Shenandoah National Park. Stony Man is Virginia's rather paltry answer to the Old Man in the Mountain up in New Hampshire. But some people, if they squint up at the western side of Stony Man, they see a face. They see sort of a notch for the eye, a prominent brow, sort of a hawk-like nose, a lip and a mouth, and then a flowing beard. All right. So that's what people see there. That actually correlates with some of these different sedimentary layers that we've been talking about. At the bottom is the basement complex. Then we've got several lava flows of the Catoctin Formation. And the notch underneath the nose, the nostrils, that's weathering of one of those volcanic breccia layers. All right, it weathers away more rapidly than the greenstone above and below it. Now, how did all this lava get to the surface? I showed you that picture of Iceland with the lava fountains coming out all in a line, and I said picture a crack underneath that. We can see those cracks. We can see them in Shenandoah National Park, and we can see them in Ivy Creek. All right, so check this out. This is one up on Skyline Drive near the Little Devil Stairs overlook, and this is a feeder dike of the Catoctin Formation cutting through basement rock. So on the left side of the screen, left side of the photo, that's granite gneiss. It's around 1 billion years old. On the right side, that's granite gneiss. It's around 1 billion years old. But cutting through it is a little seam of basalt. All right, so that's a crack that opened up around 600 million years ago, had liquid rock coursing through that crack, making its way up to the surface to feed those surface lava flows of the Catoctin. But then the crack got sealed shut by that same molten rock. All right. These cracks are found all over the place in the Blue Ridge. This central image here shows a geologic map, a portion of the geologic map of Shenandoah National Park by Tom Gathright. And the different colors represent different rock units. Pedlar granite gneiss, Old Rag granite. The dark green here is the Catoctin Formation. But what I want you to zero in on are the little lines. Those show the orientations of all these feeder dikes. Here in the image over on the right, I've taken away all the distracting imagery and just shown you the orientation of all those dikes. So north is sort of to the upper left here, and that means, well, what I hope will jump out at you is that they're all lined up in the same direction, right? They're not randomly oriented. There's like one oddball here, but the rest of them basically all line up on a trend that runs from the northeast towards the southwest. And so we think that's the direction the Iapetus Ocean opened up in, right? That was the direction that was perpendicular to the stretching that occurred as the Congo Craton moved off to the east and North America moved off to the west. If you've ever hiked Old Rag Mountain, you've walked through these feeder dikes, all right? So these feeder dikes make these very distinctive staircase-like features on Old Rag Mountain. So you got billion-year-old rock on either side, and you're walking through volcanic plumbing underfoot. Cooling columns have developed here, except they're horizontal rather than the ones I showed you earlier, because in this case, it's losing heat out the sides of the feeder dike. Pretty cool. Okay, so where can you see this at Ivy Creek Natural Area? Just downstream of the granite outcrop I showed you is another outcrop. This one right here. If you get up close to that, you will see that it too is a basalt. So on a fresh surface here, there seems to be a fresh surface on this upper corner. You see jet black rock, you see a few little amygdules in there. It's very fine grained. That is part of this volcanic plumbing system that oozed lava out all over Virginia when Rodinia broke apart. Okay, so that's right there. Martin's Branch. Okay, so we break apart Rodinia. Whew, that was quite the job, but we got it done. Now what happens next is things calm down, all right? And as far as Virginia's geologic history is concerned, Virginia goes into quiet mode, right? Virginia is also in quiet mode today, all right? Today, Virginia is not on the edge of the tectonic plate. It is on the edge of the continent, but the edge of the tectonic plate is in Iceland or in San Bernardino County, California, all right? So you've got to go a long ways before you get to the edge of the plate. So you can see here that what happens is Virginia cools off and subsides. It drops below sea level, and sea level rises all over the North American continent. This creates a vast, shallow inland sea. We call this sea an epyric sea. And the specific name of the Epiric Sea that formed in early Cambrian time in Virginia is called the Sauk Sea. The Sauk Sea is the very first of 6 major floodings of the North American continent that take place over the ensuing 500 million years. All right. So the Sauk Sea started to rise in the Neoproterozoic. It reached its apex in the Cambrian, and it subsided by the ensuing period, which is called the Ordovician. All right, that is recorded in the Blue Ridge stratigraphic sequence. So above the Catoctin Formation, there's a layer of, actually a set of layers of sedimentary rocks. All right, these are called the Chilhowie group, and they consist of, respectively, from bottom to top, the Weaverton Formation, the Harpers Formation, the Antietam Formation, and at the very top, the Tomstown Formation. You don't need to remember those names. I'll show you pictures of each of them here in a second. But what I want you to know is that we interpret the Weaverton Formation as river and beach deposits. The Harpers Formation is interpreted as lagoon kind of setting, depositing mud, something maybe like Pamlico Sound off of North Carolina. The Antietam Formation is very clean, very mature beach sand. And that would be something like the Outer Banks of North Carolina, right? A barrier island complex. And finally, the Tomstown Formation will be something like Florida or offshore of Florida, where there's no sand, there's no mud, there's no gravel. Instead, it's just basically crystallized seawater, all right? What we call limestone, all right? So we're going to take a look at these. We know how old they are based on fossils, all right? So there are fossils of this animal called a trilobite. A trilobite, it's got a central lobe, a left lobe, and a right lobe, so 3 lobes for tri. And this kind of trilobite is a distinctive kind with a really petite hindquarters. It's got a tiny hiney. So this tail plate of the trilobite is called a pygidium. And these early trilobites have very small pygidia. Later trilobites have bigger ones that sort of match the size of their heads so they can roll up like a pill bug and protect themselves when they're threatened. But this kind is distinct to the Cambrian, so we know how old it is. All right, now let's consider these different sedimentary layers. And I want you to think about them as a nearshore to offshore sequence on the margins of ancestral North America. So if you went back in time to say 500 million years ago, and you waded into the water here in Virginia, you might start going down a river that has gravel and sand moving through it. That would be the Weaverton Formation. Then you'd get to the sea. You'd have to swim across a lagoon where mud is being deposited because it's calm water in that lagoon. That's the Harpers Formation. You'd have to get out and clamber across a barrier island like the Outer Banks. That's the Antietam Formation. And then if you swim far enough offshore, you get away from the sedimentary influence of the land, and no sand and no mud makes it out that far. And that's where the carbonate or the limestone will be deposited. Now, maybe you don't feel like taking a swim that long. That's going to be a swim of about 100 miles. All right, so I get it. All right, you're feeling a little lazy. And so what you'd prefer to do is just hunker down and let these various sedimentary layers come to you. Well, you're in luck. As sea level rises, all these different sedimentary layers track with the shoreline going further and further inland to the heart of the North American continent. So the oldest layers are those river gravels. Then you get your lagoon muds on top as sea level gets a little higher. Then your barrier island beach sands when sea level is a little higher still. And when the shoreline is off in some place like Ohio, that's when limestone gets deposited here. Okay? So that vertical sequence tells us a story of sea level rise. Here are a couple pictures of these different rock units. This is the Weaverton Formation, one in the western Blue Ridge here on the right, not so metamorphosed, one in the eastern Blue Ridge here on the left. That one's pretty thoroughly metamorphosed. It's a quartzite now. Here's the Harpers Formation at its namesake, Harpers Ferry, West Virginia. So this is a mud rock, and you can see the bedding layers dipping down towards the lower right. The Antietam Formation is really distinctive. It's a very pure quartz sandstone, no feldspar in it whatsoever, and it's just shot through with gazillions and gazillions of little things that look like soda straws. These little soda straws are scolitos. Scolitos is the name for a trace fossil, a burrow of some creature that lived in this sand before it was turned to sandstone. So maybe a worm or something like that. The previous picture showed you the scolithos from the top down, so it looked like a little circle. Now we're looking at them from the side, so it looks like a line. All right, so this is like a sideways view of these ancient worm burrows in these Cambrian age beach sands. These often occur in cobbles. Because the sand is very quartz rich, these cobbles are very durable, and so these are often used as landscaping elements. You may have seen them around. Next time you walk past some gravel around a building, going to the doctor's office or the grocery store, or coming here to Piedmont, Virginia Community College and looking at our landscaping, you'll see these little worm tubes running through the cobbles. Each one is a fossil. All right, finally we get up to the top of the stack in the Tomstown Formation. It's limestone. I don't have a great picture of the Tomstown Formation in outcrop, but here's a really messed up version of the Tomstown where it's been all folded up by later Appalachian mountain building. I want to point out that these layers recording sea level rise in Virginia are not unique to Virginia. Sea level was going up globally at this time. This is a look at the stratigraphic sequence at the bottom of the Grand Canyon in Arizona. You've got some igneous and metamorphic basement rocks. Then there's an erosional surface along which geologic time is missing. And then you've got sandstone topped by mudstone, topped by limestone. Now you're missing the intervening Barrier Island beach sands here, but that's okay. Barrier Islands do not wrap all the way around North America like the rings wrap around Saturn. Okay, so that's a local phenomenon. But we know that these are the same layers because of the fossils they contain. Remember that trilobite I showed you earlier? That one's called Olanellis, all right? The one with the itty-bitty pygidium, all right? And Olanellis is found in these muddy layers in Arizona at the same time it's found in muddy layers in Virginia, all right? So the Bright Angel Shale, same age as the Harper's Formation. And it's not just Arizona. If you go to Scotland, you see this same sequence, all right? So this is in the Northwest Highlands of Scotland. They have that same erosional surface, and then you've got a sandstone on top of it. They've got this layer called the pipe rock. Guess why it's called the pipe rock? It's got a whole bunch of little scolithos going through it, all right? And then overlying that is this mud rock, the fucoid beds with trilobites, including Olanellis. And on top of that, there's some limestone. So it's the same basic sequence. So we got it in Virginia. We've got it in Scotland. We've even got it in places like Wyoming, all right? So all over the world looks like sea level is rising and depositing a very similar package of sediments as it transgressed onto the continents. Okay, it's time for us to move into our third and final phase, which is making the Appalachian Mountains, killing off the Iapetus Ocean, and building Pangaea, the greatest supercontinent the world has ever known. So to recap where we've been, we had the Grenville orogeny, which made Rodinia. Then we broke up Rodinia through an episode of rifting, opening the Iapetus Ocean. I'm going to skip over these mountain building events, the Taconian and the Acadian orogenies, because they're not well recorded in the Blue Ridge. And I want to skip right to the Alleghenian orogeny. This is the third and the final phase of Appalachian mountain building. And this is the one that makes the Appalachian Mountains big, makes them Himalayan, makes them tall and powerful, and completes the assembly of Pangaea. And then later Pangaea will break apart, and then we get modern day Virginia. Okay, so the quick summary of today's talk is this. All right, pretty simple. All right, so here comes Africa. All right, Africa is closing off the Iapetus Ocean. It smushes up the last of the Iapetus Ocean, crunches into North America, and raises up a mighty chain of mountains. That mighty chain of mountains is the Appalachian Mountains in its vigorous youth. This completes the assembly of Pangaea. So the Himalayas come back to Virginia again, all right? And again, we have rocks that record these high pressures and high temperatures that form at the roots of mountains like the Himalaya. So here's a series of little cartoons. These were drawn by Tom Gathright, the guy who did the Shenandoah National Park geologic map I showed you. All right, so here's Gathwright's depiction of the Catoctin Formation erupting on top of the Swift Run and Lynchburg formations. And these hills here represent the eroded roots of the Grenvillian Mountains. That lava basically smothers the landscape. It floods the landscape with basalt. And then we get this episode of sea level rise recorded by the Weaverton Formation, which is these rivers draining those Grenvillian foothills. And then we get this lagoonal mud, which is the Harper's Formation. Sea level rises some more. We get these barrier island sands that make the Antietam Formation. And when sea level is at its highest, we deposit this limestone that makes up the Tomstown Formation and a lot of the other stuff you see out in the Shenandoah Valley. So that's the undeformed version. But when Africa hits North America, it takes all of that and it crumples it up. It folds those rock layers and it faults those rock layers. A fault is what we call a break in the crust along which movement has occurred. So there's a big break in the crust underneath the Blue Ridge, underneath my feet here right now. And if I were out in Waynesboro, not so far underneath my feet. And that has caused these Blue Ridge rocks, the basement rocks, the Catoctin, the Chilhowie group, to move up and to move to the west. So they probably started off somewhere around Richmond, all right? And then they got shoved into their current position because Africa shoved them there, all right? Which is pretty profound, all right? Charlottesville wouldn't be where it is today if Africa hadn't shoved it into place around 300 million years ago. This is when our basalt turns into greenstone, because this is when the temperatures and the pressures go up, all right? Not only that, but within the Catoctin Formation, we see fantastic deformation. This is my son, Baxter, here, looking very, very surprised. We're in the Blue Ridge Tunnel. This is a new county park that connects Nelson County to Augusta County, right through the Blue Ridge, goes underneath the Blue Ridge Parkway. And what you're looking at here is Catoctin Formation. A lot of it's sort of a rusty color, but then you can see there's a pronounced foliation dipping to the right. The right side of the screen here is east. The left side of the screen here is west. And then there are these big lozenges that are kind of a toothpaste green in the background. I'll outline a few of them there. Those are sandstone layers within the Catoctin Formation that have been stretched into these little sausage-like chunks, and we call those boudinage. If you go down to New Orleans and you order a boudin, they will give you a sausage. All right, and so again, some geologists forgot to pack their lunch. This time they didn't see almonds in the rock, they saw a string of old-fashioned sausages. All right, so that's a stretching phenomenon that occurs in these rocks. Another thing that happened at that time is all this tectonic stress caused the rock to break, and then fluids to heal those breaks time and time again. So as a geologist, I get tired of people asking me about two things: meteorites that they claim to have found in their backyard, and quartz. There's a lot of quartz in our area, and there's a lot of quartz at Ivy Creek Natural Area, and it's okay for you to be excited about quartz, but just don't ask me about it. So what this quartz is this white colored rock, and it's called milky quartz because it's got little tiny bubbles of water trapped in its crystal lattice, and those refract incoming light, so it scatters it, makes it look white to our eyes. We can't date this directly, but it's probably around 300 million years old, which is when this Alleghanian orogeny occurred. This quartz would have originally been emplaced in something that looks a lot like those Catoctin feeder dikes. It would have been a tabular mineral mass that is essentially healing a crack. It's sealing a crack shut, all right? And then when those things get brought up to the surface, the surrounding rock, which is all rich in mica and other unstable minerals, it rots away, and the quartz is what's left behind. So this is almost always the most obvious thing that you can find. At Ivy Creek, there's actually a couple of really nice examples where you can see the edge of one of these quartz veins, and you can see broken up fragments of rock that fell into this void space when the rock was shattered. And then the quartz formed all around those little fragments. So it makes a kind of fault breccia, all right, kind of like the volcanic breccia we talked about earlier in terms of its texture. This one here is foliated, all right, so this one must have cracked open, hot water with quartz dissolved in it, sealed the crack shut with quartz, and then later it got sheared, and that shearing imparted a foliation to it. So this would probably be an Alleghanian age foliation. All right. I promised you a quick little detour up to Newfoundland. I've already taken you to Scotland and Arizona, so let's go to Newfoundland too. This is my wife and my son walking towards a big lake in western Newfoundland. All right, this is on the big prong that pokes up towards L'Anse Meadow, where Leif Erikson made his colony, but it's called Gross Mourne National Park. And if you go there and you've learned Blue Ridge geology, you will feel right at home. It's obviously a more spectacular landscape. So here's like one of the little tour boats that takes people out across this lake. Those are pretty big cliffs soaring up above that lake. That's not Ivy Creek Natural Area. But the rocks are, all right? So what these rocks are is these are Grenvillian age granites and granite gneisses. And cutting through those granites and granite gneisses, we have feeder dikes of 600 million year old basalt. All right, so it's basically the Canadian equivalent of the Catoctin Formation. And not only that, it's been shoved up on a thrust fault going up, going to the west, on top of Cambrian and Ordovician carbonate rocks. It's exactly the same thing. It's just been glaciated, so it looks a lot better. All right, I want to conclude my talk today by talking about the most intriguing rock at Ivy Creek Natural Area, and that is this one. This is a rock that I first noticed when I first went to Ivy Creek about 3 years ago. And when I saw it, I was like, wow, that's really interesting. That's like a breccia. It's got chunks in it. So I'll just trace out a few of these chunks. Here's a chunk. Here's a big chunk. Here's a little gray chunk, another little gray chunk. Here's another little gray chunk. This little green thing here that's really smooth, that's a lichen growing on the rock, so don't mistake that for a chunk. But then you can also see a bunch of open holes, vesicles, all right? So this looks to be a rhyolite breccia. So what's a rhyolite, you ask? It's like a basalt, but it's silica rich rather than iron rich. So it's again a volcanic rock, all right? And this volcanic rock evidently flowed over some pebbles and picked up those pebbles, and it degassed, making those vesicles, but it's got a very different composition. So the question I wanted to know is, how old is this stuff? If you want to see this for yourself, it's right here near the hydraulic overlook on the Purple Trail, really close to the twin bridges that go over the reservoir. And there's a bunch of it scattered all over the ground there. So I reached out to my friend and colleague Chuck Bailey at William & Mary, who's currently in Oman, but he took the time to reply to my email and was like, yeah, that's a weird rock. And I actually had a student map that and they dated it. And the date that came back was 111 million years old. Now, you might be like, why is he so excited about that? Well, that is a Cretaceous age, and it doesn't match anything else around here. It's totally bonkers anomalous. And so that's really, really, really interesting. Why do we have felsic volcanism in Albemarle County 111 million years ago? To illustrate how weird this is, I want to show you a piece of student work. This is a timeline that one of my UVA students created. Each summer I teach a Geology of Virginia course for the University of Virginia. And this summarizes some of the things that we've talked about and a lot more. You're just getting the tip of the iceberg here today, people. So there's the Grenvillian orogeny, right? The various phases, the Shawinigan, the Ottawan, etc. Here's the breakup of Rodinia, the eruption of the Catoctin Formation, the deposition of the Swift Run, and here's the Alleghenian orogeny where we make Pangea, all right? And then this little blank spot over here, that's when apparently we had felsic volcanism in Albemarle County. Who knew? I did not know that prior to preparing this talk. I am really, really surprised by it. I'm really looking forward to learning more about what the heck was going on here 111 million years ago. So with that, I will conclude my remarks. I want to point out that there are opportunities for you to do more geologizing. Some students and I are going to start leading geology hikes at Ivy Creek Natural Area, and I hope you'll be able to join us in going and looking at some of these rocks and hearing us maybe repeat some of these key points that have overwhelmed you today. And if you're up for it, I offer a series of field courses here at PVCC in the summer. So this summer, I am planning on offering field studies in geology in Shenandoah National Park, a field studies in geology for Albemarle County, and a field studies in geology for the Massanutten Synclinorium out in the Great Valley. These will all be one-day field classes. And then we'll have an overnight field class as well that goes out to the exceptional outcrops along this new superhighway to nowhere called Corridor H in West Virginia, which has really, really, really great geology worth going and traveling to. So keep your eyes open for those, check our schedule of classes, and I look forward to answering what I hope are some really excellent questions. Thank you.
Thank you, Professor Bentley. We don't have any questions in the chat, but if anyone wants to unmute themselves and ask a question, we'd be happy to answer those. Oh, here we go. Here's one.
All right, so the question in the chat is, do the striations in the granite and ice come from gravity pressing down or plate movements pushing sideways, or both, or neither? Yes. Principally, they're coming from the plate motions pushing sideways. It is more complicated than that, but that's a good place to start thinking about it. Think about a messy desk. Like, in fact, I have a messy desk right here. Look at all those papers all over my desk. If you put your hands on either side of that messy pile of papers and you push them together, the papers would take on a new orientation perpendicular to your squeezing direction. That's the best way to get a foliation. It's not the only way. You can also get it through faulting, but I don't want to muddy the waters here. I guess I'll say this. Geology is not rocket science. And by that I mean rockets are simple, all right? You have various equations about force and lift. You put the pieces together, you light it on fire, it goes to the moon, all right? Geology is much more complicated. There's a lot of different ways things happen. We understand some of them pretty well, some of them okay, and then some of them maybe we don't even know about. And so it's a big, complicated mess. This is a complicated place with a lot of different moving parts. They've been moving for 4.5 billion years. And so it's complicated. All right, so I'll leave it at that. Next question. Hey, Lindsay and Boone. All right. Good to see you guys. How long did it take for the mud, which was hot and agitated, to become mica? Yeah, so rates of metamorphism are controlled by a couple of things. One is the temperature, another is the pressure, and then another is whether you've got water there. So water helps facilitate chemical reactions in many cases. And so if you've got a really dry mud, you're probably not going to get a bunch of mica. But if you've got a really wet mud, you can make it happen more rapidly. So the answer is, it depends. Again, it's complicated. All right. I think you can unmute yourselves if you want to ask a question and just shout it out.
I just wanted to say that geology is not a static science. It keeps changing.
Yeah, that's how I feel preparing this talk. Like, I thought I knew everything there was to know about Blue Ridge geology, and suddenly Ivy Creek Natural Area throws a 111 million year old rhyolite in my face.
I took geology in 1959, first time around, then in New York City. And just the whole idea of plate tectonics was just happening then. Then we moved down here, and in Nelson County, there was a geologist named Keith Fry, and he would talk about the orogenies that had happened. And he happens to be gone now. And now we decided to check out this, and suddenly you're talking about a whole new batch of things that weren't even talked about before.
Yeah.
And it's kind of changed my idea of geology greatly.
Awesome. Great. Well, thanks for sharing that. Yes. Science does not sit still. All right. Yeah. We continue pushing the boundaries, exploring, finding new things, attempting to grapple with those new data and incorporate them into our thinking, which always has to be provisional, right? We always have to be able to willing to throw out our cherished conclusions if we find new data that doesn't agree with them. All right, we got some more questions popping up in the chat, so I'm going to go back to those. John asks, could your rhyolitic breccia be associated with the rifting and opening of the Atlantic Ocean? Although rifting is associated primarily with basaltic lavas, there can also be minor silicic volcanism. This also occurs in Iceland. Yeah, that was another thing that surprised me. When I was in Iceland, I came around a corner with just jet black rock after jet black rock, and then I saw granite, and it blew my mind. That's kind of like how I felt earlier this week when I found that rhyolitic breccia. So John, that's a great idea. The issue is that most of the rifting associated with the breakup of Pangaea and the opening of the Atlantic is earlier. It's Triassic and Jurassic. And yeah, none of it seems to slop over into the Cretaceous that I'm aware of. In fact, like really what we have in the Cretaceous is just a bunch of river gravel. It looks like a really nice passive margin. And so I'm really, really surprised by that result. Okay, so I'm seeing some other questions. Daisy, hey Daisy, I'm glad you're here. What would the process of figuring out the volcanic rhyolite mystery look like? Well, I would want to repeat the dates and verify that those numbers are real before we get too excited about them. Actually, it's probably too late. I'm already too excited about it. But at any rate, I think that would probably be the first step. And then Susie and I have talked about some other steps to get a closer look at the textures and how they relate. So yeah, Daisy, the other steps might be up to you. You can think that through. Which way is Virginia moving now due to plate tectonics? Well, we're still moving westward. And as we move westward, we're basically pulling about 1.5 centimeters further away from Africa and Europe every year. And Africa and Europe are pulling 1.5 centimeters away from us every year. So there's a net widening of the Atlantic of about 3 centimeters every year. And we're running into other stuff over on the West Coast as a result. So the West Coast is now the leading edge. Go to Seattle, if you don't believe me, and look at the giant volcanoes rising up within view of that major metropolitan area. That is where the new convergent margin is located. Okay, I've got thanks, Mike, for your note. I'll go ahead and gloss over that for the moment. Alex asks, can you talk about the Mitchum's River? Any brief geology? I live off it. There are pictures of yours of stones from there and near Batesville. Okay, so, and he's found a lot of milky quartz that he won't talk to me about. Good, yeah. Talk about the milky quartz with someone else. Yeah, so the Mitchum's River Formation is the sort of Lynchburg group equivalent that's in the central Blue Ridge. And there's some differences between the rocks to the west and the rocks to the east, so it gets its own name. It is the main thing that you see outcropping on the Mitchum's River in Albemarle County. I haven't explored it much in any other place, but I've seen it in a few spots. And yeah, it's all basically a bunch of sand and mud that was shed off of Rodinia into the Iapetus Ocean. Then it was all metamorphosed during Appalachian mountain building. Okay, another question comes from Bethany. As an educator, how do you address with students, especially non-geology majors, why the study of M or B, million or billion-year-old rocks and formations matter? Yeah, that's a great question. I mean, everyone has to kind of come to their own answer for this, I reckon. But I mean, I suppose you could couch it in sort of practical terms, like by understanding the whole system, you can understand how oil forms or iron ore forms, and then you can be like, and you can sell oil and iron ore, and therefore, because you can make money off of it, it's worth knowing. I would offer kind of a slightly different perspective, which is that I find it really philosophically validating. I really like knowing that I live on an old planet and on a dynamic planet. It keeps me interested and engaged. It also, kind of puts me in my place. I like the feeling of insignificance that comes with, living on a 4.6 billion year old piece of rock. The little sort of dramas and foibles in one's life don't seem to matter quite as much when they're stacked up against geologic history. I don't know, that probably wouldn't appeal to some people, but that's kind of where it lands with me. David Smith, I see a hand raised.
I'm on mute, yes. This is actually Marilyn Smith, David's wife. So I used to be on the Ivory Creek board. And at the time, I don't know if you're familiar with Tom Deerhoff's work, but he noticed a lot of patterns in the agricultural history of the property that he thought was geologically related. And one of them was the rhyolitic breccia, because they couldn't grow any crops on that rock. Because that rock is really hard and doesn't form any soil. And both JMU and William and Mary came out, their students came out and they mapped it and they mapped the faults. And JMU also did some age dating. It came out a little bit different for the breccia is 157, but the xenoliths came out as 750 million. So the age of the Robinson granites. So,
Cool. That's great.
Yeah.
Well, that's all new to me. And so that's really, really interesting. Thank you for
Right.
sharing that.
Mhm.
Clearly, I've got some digging to do.
Right. And if you had any students looking for projects, I think if they looked at Tom Deerhoff's report and showed how different plant communities have developed, you'd find differences in the rocks.
Cool. Thank you for sharing.
You're welcome.
All right. Other questions? If anyone else is raising their hand, I can only see, one screen at a time. I guess no one else is. Everyone else is just silently waiting for someone else to ask that perfect question. Okay, well, going once, going twice.
Okay, well, thank you for doing this talk this evening. This was very interesting and very informative. And I want to thank you all for spending your time with us this evening. We hope that you enjoyed it and that you learned a lot. We hope that if you have not visited Ivy Creek Natural Area and Historic Riverview Farm, that you will do so soon. And I just want to let you know about 2 Ivy Talks that we have coming up in February to celebrate Black History Month. The first one will be with David McCormick, and he will discuss African-American fiddlers in Albemarle County on February 15th from 6:30 to 8 p.m. The second talk will be with Michael Carter Jr., who will be discussing the history of agriculture in Virginia from an African-American perspective. This talk will take place on February 19th from 2 to 4 p.m. You can sign up for those events just like you did for this one at ivycreekfoundation.org. And as always, these talks are free and open to the public. If you enjoyed this talk and you would like to support what the Ivy Creek Foundation is doing for our community, please consider going to our website and becoming a donor today. Otherwise, thank you all for joining us and have a great rest of your evening.